Alright, so we're going to actually start off related rates with some basic questions. These are taken from your book, and I believe your homework for number 16 is numbers 1 through 12. I'll be doing numbers 1, 2, and 3 in your notes. So in your notes packet, 4.6.1, starting off, says the radius r and area a of a circle are related by the equation. Write the equation that relates dA dt to dr dt. It says a lot more words than you need it to say. Really, they're just asking you to find dA dt. So, the variable with respect to is t. So we get that the derivative of a with respect to t is equal to 2 pi times r times dr dt. And that actually is the answer. So like I said, a lot more words for something pretty easy. Number 2, surface area. So relating s to r with respect to t though. So ds dt is equal to 8 pi r times dr dt. Alright, number 3, we have the radius. Okay, so letter A, you want r to be a constant. What that does, I'm going to rewrite it here, it makes this whole piece a constant. So if we're doing this with respect to t, this one's pretty easy. We bring down our constant, multiply it by the derivative of h, which is our only variable, with respect to t. So that one's done. But letter B, now h is constant. So v is equal to, and I'm going to rewrite it so that the h is with the pi, and then times r squared. Same rule as before. Bring down the constant multiple, and then multiply it by the derivative of r, which is, r squared, which is 2r, times dr dt. And then part C, is our most complicated one. Neither of them are constant. We've actually done this problem already. So if neither is constant, it's a pain because now we got to do a product rule. So dv dt is equal to, we did this problem in worksheet 4.6.0. Leave the first one, derivative of the second, plus leave the second one, derivative of the first. And that would actually be our answer, which is the most complicated of the three. So what I want you to see is that related rates, we're really going to get used to taking the derivative with respect to time. And now we're going to go through what a related rate actually is. So, let's see if this problem showed up properly. Okay. So this is a nice beginning related rates problem. So why do we call it related rates? There's always going to be a situation where objects are moving. So in this case, this ladder in red is against the wall if its bottom is being pushed or pulled at a constant 1/2 meters per second. How fast is the ladder top sliding when it reaches 5 feet, 3 feet, 1 meter up the wall? Or meters, all meters. So what I start with is a sketch. And the sketch is really important because it gives you an idea of what's really happening. Now, I gave you a picture here. Let's just start out with the ladder being pretty far up the wall. So why is your sketch so important? Well, it gives you an idea of what relationship we'll be using. We know that the ladder is 6 meters. And it starts to slip down, let's say. So as we have the ladder slip down, we do a consecutive 3 pictures or 3 sketches of 3 different times. So that's where the time piece comes in, because you're going to notice in the problem itself, we really don't use time, but we talk about time. And we do our derivative with respect to time. So in this problem, the ladder is 6 meters. It's sliding down the wall. And what you want to figure out is what is constant. Well, the ladder never changes size. So this 6 meters is actually a constant, meaning in each of the pictures it never changes size. Now, anything else that's not constant, then we can label. And I like using x and y. X's I usually use across, y's being up and down. So we'll start with that. Now, this really tells you a lot of what you need to know. It gives you an idea of what's constant. And that's going to be really important. So that's going to be the first thing that we do, is try to make a sketch that shows us what's going to be constant, what's not. Sometimes we end up with no constants at all. Now, next thing we do is we look in the problem, and actually I'm going to start you a little differently than last year. We're going to start with the question. So what is it that they are asking you? How fast? So that word how fast tells me it's a d something, dt. How fast is the ladder top sliding when it reaches 5, 3, 1 meter up the wall? So are they talking about the x variable or the y variable? If we're talking about the ladder sliding up and down the wall, we're really talking about how fast it's moving up and down. So that's the question. Now, along with the question comes the instant at which they want to know about that ladder sliding. And there's actually 3 different questions in here. We're only going to focus on 5 meters. Okay? So we want to know dy dt, the instant that y is 5 meters. Why is the instant so important? A related rate question says, watch the ladder slide, but I'm going to ask you a question when I take a picture of the movement. So what does that mean? You have this value here, and the reason I make you do the sketches and then we go straight to the question in instant, I need you to understand that this value is not a constant value. And how do I know it's not constant? Because the y value here, here, and here is not always 5. It changes. Okay? Next, we're going to go through and we're going to figure out what the given information is. So, what have they given us? Now, we have the 6 meter ladder, but we've already figured out that that's a constant. We use that in our picture. We have the bottom being pulled or pushed, and in this case I'm going to tell you that we want the ladder sliding down, so let's do arrows of motion, which means if that goes this way, then the x would slide that way. In each of the pictures that would be true. So we know that the bottom is being, let's say, pulled, it would be the easiest way, or sliding out at a constant of 1/2 meter per second. So let's look at that 1/2. Yes, there's space there for a reason. Meters per second, because I want to look at units. So remember when we talked about differentials and units? I can tell right away, because the bottom is seconds, that this would be a dt. And the top is a meter, which is a distance. Whose distance is it? Well, we already were looking at the motion. It's x's motion. And then the one last question, is the 1/2 making the x get bigger, or is it making the x get smaller? In this case, since we're making the motion this way, it would be positive 1/2 meters per second. So here's what's given. Next piece. After you organize all your information, so you learn that even in physics, you organize all the information you're given and try to make it fit into a formula, and that's essentially what we're doing. In this case, the formula is going to be the last thing we figure out. What formula do we know that relates all 3 sides of a right triangle? That should be pretty easy for you. A squared plus b squared equals c squared. So I'm using x, y, and z in this case. I'm just calling the third side z. And what we can do right away after the formula, you can substitute constants. And there is a very, very specific reason why we're allowed to put constants in right now. Right now we're saying this is generic motion. This relationship, x squared plus y squared plus z equals z squared, represents the motion of all 3 pictures. And I want that generic motion to be represented by the formula. Therefore, This instant number is what usually confuses everyone, the 5 meters. That's not generic. That's not something that happened in all the pictures. So the only value that I can substitute in right now is the 6, and the 6 was our z. So x squared plus y squared is equal to 6 squared. And that's our generic formula, which I'm going to make it look a little nicer and easier. And once we've substituted in all the constants, all constants are in, the very next step is then take derivative with respect to t. So we're going to take the whole entire equation and take the derivative with respect to t. So we had a little practice with this. So 2x dx dt plus 2y dy dt is equal to 0. And then we go back to our information. We know the question is this guy, and the only way I could solve this is if I know dx dt, which we do. And what I'll do is I'm going to highlight the ones we already know. So we know dx dt. We're good here. We know that the instant is when y is equal to 5. Okay? So the only thing we're missing is that x. And so a lot of talking for this one problem, right? What I need you to understand is the second that you take the derivative, here's where you can do an instant picture. So I took the derivative, which means I took the picture at the instant when, well, the ladder never changes at 6 meters. The height was 5, and the x I don't know. You're allowed to use the 5 now because we're talking about the instant that this is happening. So this is the time in question. So obviously I can find x by using the formula, Pythagorean theorem. So we get that x squared plus 25 is equal to 36. X squared is equal to 11, therefore x is equal to the square root of 11. It would be plus or minus, but since it's a real world problem, I'm going to use the positive. So what do we end up with? We end up with using this x equals root 11, this value, so that value we had to find. We found it at the instant when y was 5. Notice I did not do that in the beginning, and that's because it wouldn't be a generic number to all of my sketches. So 2 root 11 times dx dt, which was 1/2, plus 2 times y, which was 5, dy dt equals 0. And therefore, we have everything we need. Simplify this a little bit. And we get that dy dt is equal to negative root 11 over 10. And then here's one major piece. You're going to put the units back. Now the time units, which are at the bottom, we know we're seconds, and we were measuring our y's in meters. So that would be the units. Why is it negative? Remember the sketch that we started with, which had the generic 6, the y, and the x, because the x was moving this way, the y was moving this way. What does that mean about the y value? It's getting smaller. That's what the negative represents. Alright, so there's an actual problem done for you. What I'm going to do next is go through what did we do to get our answer? What are the steps you want to take? So in related rates, we're going to start off with number 1, a sketch at 3 different times to identify constants. Okay? The second piece, so that's the first thing we did. Then, I'm going to go back a little bit and kind of rewind you back. After our sketches, we figured out what was the question. What are they asking you? And then on top of the question, we also figured out what's the instant that they're asking you the question. At a specific time, they're taking a picture of the motion. What's happening at that specific time? The third thing we did was the given. we organize the given information. In the given information, you want to label constants, and here I'm going to even put a note for you. Oopsie. Ignore the instant because we already had it labeled above. We did it right there, so we don't really need to relabel that work again. After we did the after we did our givens, we figured out our formula. So, formula that relates to our sketch, and in our formula, enter constants only. So once we did that and we kind of related everything we needed to, we were able to then take the derivative with respect to t. And once we did that, we then had to, blue again. Identify any information, any unknown info using original, formula, at the instant. And how do we do that? We do that by taking the derivative and we actually do an instant sketch. And this is where we would use that given that information from step 2. That instant from step 2 would be used in our picture here. Alright, so other things, important formulas. So these are probably the formulas that we're going to use. So right triangle, when you're talking about all the sides of a triangle, we're going to look into, let's see. If we know all the sides, Pythagorean theorem, a squared plus b squared equals c squared is probably going to be our most common. Other things that we might have an area, 1/2, base times height. Now in the right triangle with an angle, that's when you start thinking about SOHCAHTOA. Additionally, we could be looking at area. 1/2 AB times the sine of C. The C is the angle in between A and B. So that might be important. We've also used, and actually this says right triangle, and here this formula works for any triangle, I should have said. Sphere, we have surface area of a sphere, which would be, let's start with volume actually. Volume is 4/3 pi r cubed. When you take its derivative with respect to r, you get 4 pi r squared, which happens to be the surface area. A cylinder, same thing. Let's start with volume. Pi r squared h, two variables. Keep that in mind. And then the area, for some reason, if we were asked about that, top and bottom, two areas of a triangle, two areas of a circle, plus the soup label, which would be the circumference times the height. So two variables again. Cone, if you have a cone, you'll only be asked about volume. That's 1/3 the volume of a cylinder. Pi r squared h. And similar triangles. I'm going to actually do a picture of that one. Let's see. Instead of doing a formula, I'm just going to write up proportion, okay? Similar triangles have sides that are proportional. So these are pretty much most of the formulas that you'll be using. I'm going to do one more example for us for today's notes, and that should get you through homework number 16. So here we go. And again, there's a lot of different questions. We're just going to do one of them. It's repetitive otherwise. So a winch, and as much as you already have a picture, you're still going to follow the steps. So first thing I'm going to do is try to make a sketch out of this. A winch reels in a rope at 2 feet per second. So the winch never changes height. It starts with the boat probably being pretty far from us, and then the boat and the winch, I'm going to move over. The winch is still 20, but the boat's starting to get closer until winch is still 20. It's very close and you can undock. So we know that this is a right triangle. We know that the winch was, I believe it was 20 feet. This is 20 feet. And so you've figured out that this is a constant. Obviously, you don't have to label all of them. I'm just getting a little repetitive. This side down here is where the boat would be coming in this way. As the boat comes in this way, then this side also gets smaller. So that's important. We know that these sides are getting smaller. I'm going to label this one X, I'm going to label this one Z, and both of those are changing, so there should be no value. Alright. Next, now that we have our sketch, let's do our question. So the question is how fast, so fast means it's a D, something DT. How fast is the boat moving? Well, the boat moves horizontally, so we know that we're talking about the X. So there's our question. The instant that the rope is 45. So I'm going to combine what we talked about before, making a sketch of the instant. Well, here's the sketch of the instant. So we want to know that this is a constant 20. The instant when the rope would be the Z, is 45 feet. Now be careful. This is an instant picture, which means we're allowed to use the 20 right away. We're going to wait to use that 45. And then here's our X. Now you can see already that we could potentially use our instant picture to find the X, and some of you will get used to doing that. I actually do wait to make sure you don't get too confused with what you're allowed to use. In this particular example, just to show you, I am going to go through and find the I can't think. I'm going to find the X right away to give you an idea and to show you the mistakes that could potentially happen. So we end up with X squared plus 20 squared is equal to 45 squared. I'm just going to shortcut this for you and use my calculator off to the side. And hopefully it's not perfect, but it'll work. The square root of 1625. This is a great place to talk about rounding. As much as the AP wants you to round to 3 decimal places, you will never round to 3 decimal places within the problem, which is why you see this root instead of me writing the decimal approximation, which would be 40.311. You do not do that. There is a chance that you could lose a point for accuracy as a result. Alright, so in this problem I actually found the instant. The instant is the square root of 1625. Hopefully I did that right. So, once we have the question and the instant, now I'm going to go through following my steps, looking back again, remember, given is the next piece. So now I'm going to do my given. So given, you're going to go back through and read any information that we haven't written down already. We already used the constant 20, the 2 feet per second. Again, we can tell that that's a differential because of the feet per second. And it's 2. Now the feet per second, the time goes with seconds. The feet has to be a distance, and we just have to see whose distance that is. A winch, reels, and a rope. So it's the rope's distance, which is Z. It's reeling in, so now we know that it has to be negative because the Z value gets smaller and smaller because it's reeling in. Alright, I'm not going to worry about the 45 because we already figured that out in the instant, and I'm not going to worry about the 20 because that's already a constant we use. So the given is to look at any other information that was given to you. Alright, so now that we have all of that, now we're in the next step, which is to write our formula. So, formula. Obviously, very similar to the last problem that we just did. The formula that we're going to use is x squared plus y squared equals z squared. And here we're going to remember to enter constants. The constant that we're allowed to use is 20, and that was our y. So x squared plus 20, don't forget the squared, is equal to z squared. So now that we've entered our constants, we can take the derivative. Okay? So the reason why I'm not even bothering with this 20 squared is because once I take its derivative, it'll be 0. So I get 2x, don't forget you're doing this with respect to t, plus 0 is equal to 2z dz dt. And things that we can do, I mean, we really can simplify this. The 0 is not really there. So I could divide 2 on both sides of the equation. And then I'm just going to substitute in everything I know. Well, we already found x at the instant. So rewinding back, we're now, after the derivative, allowed to use the instant information. So I can use the x, which is root of 1625, dx dt is the question, equals the z value at 45 feet times dz dt, which was negative 2. So dx dt is negative 90 divided by the square root of 1625, which is a good enough answer. And then we want to put units. Time was given in seconds, distances were given in feet, and that would be good enough for me. Let's talk about why you can't enter constants. Why you want to be able to enter constants before derivatives. So if a value, let's say this y, if the y is constant, when you take its derivative, the derivative is the rate of change. So if it never changes, I'm hoping you understand that the derivative would be 0. And that's why we do that. We eliminate extra variables. Because if we didn't, here's what it would look like. Let's say you said, oh, I completely forgot about the constants, and I'm not going to put the constant in. You end up with this ugly looking thing. You end up with extra variables, oopsie, z dt, and you end up with this thing. And you can still get the problem right if you understand what is the rate of change of the y. Well, if the y doesn't change, the dy dt is 0. And then you could actually substitute in 0 for the dy dt. I think that's complicated, so you enter your constants before the derivative because those are generic. It's generic information that's true all the time. You are allowed to enter any information after the derivative that has to do with the instant. So in blue right here, all of this was true at the instant that they asked you the question. So looking back at our 3 sketches, here are my x values. They're all changing. So what the question does, it says, as much as it's changing, I want you to find some information exactly at the instant when this is 45, which will be different than the instant when that rope is 30. If it was 30, your x would be different. And that's why after the derivative, after you do the rates of change, then you can put in your instant. So those are a few examples which I think should be good enough for you guys to get started on homework number 16, which will be due hopefully tomorrow, which is Wednesday. I will be preparing another video in case we're out on Wednesday at that point, you would then do homework number 17 so that we can stay on schedule. Thanks, guys. I know this sucks, but I'm working too, so I don't feel as bad.